All right, so first we are going to look at the course. Obviously, that's what you guys are seeing on the shared screen. And we are now into February. You can see I've already got stuff going on for February. We've got things linked. There's some stuff that we'll be doing today that I went ahead and linked ahead of time. So if you want to get a sneak peek, you're more than welcome to. We'll also be doing a Desmos activity tomorrow. Again, if you want to take a sneak peek at that, you're more than welcome to. There will be a class one that we do as well. It's going to be the same thing, but this is linked to a just general link to the activity. Yeah, so we have a calendar going on here. If you notice, we have everything for chapter 6 there. Whatever you've completed, because remember you're supposed to complete the assessments. Those are the only required assignments per unit. As then the classroom activities that we do in class, so you just get credit for doing them. You'll get a little check mark if it's been submitted, right? If it has not been submitted, you get this little has not been submitted. This assignment is overdue, right? And once again, I just want to make sure it's clear, you do not lose credit for turning things in late. Just you'll get graded on how you do. This is how it is. I don't believe in taking away credit for not getting it done on time. If you can show me that you understand and your work is good, you get the credit. That's how it goes. All right. Chapter 7 is open. All right. It was closed. It was restricted to only those who had completed both assessments previous to this week. It is now open. The notes and resources are all ready to go for each section, as well as the practice problem set for each section. I do not have the solutions ready yet for those practice problems. Those should be forthcoming. And then I am still putting together the assessments for Chapter 7. I have not gotten those completed yet. That's why there's nothing under Chapter 7 assessments. So the Chapter 7 module is underway. It is getting put together, and it should be completely ready shortly. All right, so that's just a sneak peek. We have these things ready to rock and roll here in Canvas. All right. So any questions about Canvas and the resources that are available right now? All right. Then the next thing we're going to do is I'm actually going to jump over to OneNote and do some examples. I'll do that in just a moment. So while grading the free response questions for Chapter 6 that had been submitted over the weekend or previously to the weekend, I did a lot of grading on Sunday night. I saw basically one major error that kept showing up in many of the responses. So I wanted to address that, and it has to do with the first question on the free response assessment. So we're going to do that. I've got a example set up in OneNote here that is very similar to the type of problem that is on the free response question number 1 of the free response questions. So if you got some comments on your free response question saying that you were incorrect in some part of question 1, you probably want to follow along to this so you can make revisions if you like, especially if your grade was not, your self-selected grade was not approved because you had errors in your work. Right? And this would be something you want to pay attention to, and if it doesn't make sense, ask questions about. Right? So I'm going to reshare my screen. Lar. Excellent. All right. And we'll do these a couple of examples. Right, so the one major error that I kept seeing was with the first free response question about the fat quarters, in which you were provided a probability distribution for a random variable x that represented the number of defects in the fat quarters, and it ranged from 0 to 4 or more. And each of those had a probability going along with it, hence the probability distribution. You were then asked to create a secondary probability distribution for another random variable y that represented the number of defects on a fat quarter that could be sold and the condition for being sold was that it had 2 or fewer defects. Right, so that actually creates a conditional distribution, right, if we want to create that probability distribution. So that's what we're going to look at. Is this example will kind of demonstrate how that should have been done. I'm going to use all right. So in this case, we have a different context than the one in your assessment. So we're going to let X equal a grade point of a student in a college algebra class. And so we have the probability distribution for X over here to the right. And a grade point is the numeric value assigned to each letter grade. Right? So we have an F is 0, D is 1, C is 2, B is 3, A is 4. This is how your GPA is calculated. Each letter grade you get has a numeric value. You add up your numeric value of your grades, divide it by the number of classes you have. There's your GPA. If a student gets an A, B, or a C, then they pass the course. This is typical for a college course, right? You need to get a C or better to actually get credit for taking the course. Otherwise, you need to take it again, especially if it's a requirement of your major. So we're going to let Y be a random variable. And we're going to have that equal the grade point of a student who passes the course. Right, so we'll start our new probability distribution. This will be Y. And Y can have values of 2, 3, or 4. Those values represent a passing grade. Right, now the major error that I saw that many of you did was that you simply took the probability of getting a 2, a 3, or a 4 from the probability distribution of X and dropped it into the probability distribution of Y. That is incorrect because that creates an invalid distribution. The probability does not add up to 1. I don't have 100%. So it's invalid. It's not a proper probability distribution. We always need to add up to 100% within our probability distribution. Otherwise, we're missing stuff. And so if all you did was take these proportions, these probabilities, and drop them into the other probability distribution, that was incorrect, and that then made what you found in part B, the mean and standard deviation, also incorrect. You got the wrong values, even if you did the right method, right? Your values were incorrect because you started with the wrong numbers. And so this is an error that propagated through your work. So in order to actually properly calculate this, we need to do a conditional probability. All right, so we have to account for the fact that only a portion of my original sample, so to say, is what I'm considering. Right, and so what that looks like is the probability, we'll start with Y equaling 2, is equal to the probability of X equaling 2 given that the student passed the course, right? And that means that X was greater than or equal to 2. So this is our conditional distribution, right? And from our previous chapters, we know that this probability is equal to the probability of X equaling 2 and X being greater than or equal to 2 divided by the probability of X being greater than or equal to 2. Okay. Now, the probability of X being greater than or equal to 2 is these 3 probabilities from our original probability distribution of 2, 3, or 4. So we get 0.35 plus 0.30 plus 0.18, and that works out to be 0.83. Okay, so this is the probability of X being greater than or equal to 2, right, that we need for this calculation. Right, and then the probability of X equaling 2 and X being greater than or equal to 2, well, there's only one option for that, and that is the 0.35. Right, there's no way for X to be equal to 2 and greater than or equal to 2 other than that. So we end up with 0.35 divided by 0.83. and that results in a probability of 0.42. And that is what goes into our distribution here. We can then do the same calculation for probability of y equaling 3. But if we notice how this worked out, right, we'll just end up with 0.30 divided by 0.83. And we get 0.36. And then the probability of y equaling 4 is 0.18 divided by 0.83. And that gives us 0.22. These decimals were obviously longer when I originally calculated them. I rounded to 2 decimal places because my original probability distribution for x was rounded to 2 decimal places. So I'm just kind of keeping the same amount of accuracy for this other distribution. And if we add up 0.42 plus 0.36 plus 0.22, we get 1. That is most excellent. That means our probability distribution is complete. We're not missing any values. Is there anything I can clarify about this part, which is basically the answer to part A of this question? All right. So this is what was expected essentially for part A of question 1 in the free response question, obviously with the values from that question and not from this question. All right. So then we move on to part B, determining the mean and standard deviation. When determining the mean and standard deviation for this discrete random variable y, there's no shortcut. There's no short way to do it. We just have to do the calculation and put it through the calculator. It's not a binomial distribution. It's not a geometric distribution. It's just a discrete random variable with a probability distribution. So we have to do all the math, which means to find the mean of y, we find the expected value of y, and that's equal to the outcomes, right? So outcome of 2 times the probability of getting a 2 plus the outcome of 3 times the probability of getting a 3 plus the last possible outcome of a 4 times the probability of getting a 4. And that is it. That's the entire calculation. There's no need to divide by 3 because I have 3 possible outcomes. It is simply the outcome times the probability of that outcome for each possible outcome added up. That gives us our mean. Right, so when we do that, we get 2.8. So that means essentially the expected grade for a student taking this college algebra class, right, over time. Like as we have many students taking the course, we would expect the average grade to be about 2.8, which is probably like a B- or a high C+. Right. When finding the standard deviation of y is equal to the square root of the variance, which again, there isn't a shortcut for this. We have to just push the math through. And for that, we get each outcome minus the mean squared times the probability of that outcome plus 3 minus 2.8 squared times 0.36 plus 4 minus 2.8 squared times 0.22. All of that is under our square root sign. You are more than welcome to just put this in the calculator exactly as it looks here and do it in one calculation. That is actually more recommended because it will result in the least amount of rounding error. If you do each part of this individually and then take the square root of it, you're going to have more of a rounding error possibly, depending on if you're rounding in between steps. If we do this and we push it all through the calculator in one shot here, we get 0.0 7, 7. So we would expect, right, over many students taking this course, the students who pass, their grades will vary by about 0.77, or about a little over half a grade, right, from the mean of 2.8 on average. And so this is what essentially the work for parts A and B of question 1 should have looked like. Very similar to this. Is there anything I can clarify? Okay. So that leads us to the last part of question 1 from the free response questions, and that has to do with a linear transformation. Right? That's what part C was supposed to be about. Now, part C in question 1 in the free response questions was occurring within the same context. You were still talking about fat quarters. It was just another company that was selling fat quarters, and it was providing their selling price information and how they calculate the selling price of these fat quarters. The results that you got in parts A and B did not carry into part C. You didn't have to use those results. So even if you got parts A and B wrong, you could have still gotten part C right, because it basically is its own problem. It lives on its own. Just had the same kind of context. So this again is supposed to kind of mimic the same type of process you should have used for part C. In this question, we have the mean and standard deviation of the number of defects on a computer chip made by chipcore are 1.2 and 0.36. That means the 1 point respectively. So 1.2 is the mean, and 0.36 is the standard deviation. The chips sell for $25 each, but are discounted, subtraction, by $275 per defect. All right. We're trying to answer what are the mean and standard deviation of the selling price. Right? We want selling price for the computer chips sold by Chipcore. Right? Before we can start this calculation, we need to identify our random variables and how they're related and what's the information we know. Right? So to start, we're going to let C equal the number of defects on a chip sold by Chipcore, and we're going to define the random variable S to be the selling price of a chip sold by Chipcore. We also know that the mean of C is 1.2, right? And this is the number of defects. And the standard deviation of C is 0.36 defects. All right. Lastly, the random variable S is equal to, right, the selling price, 25 minus 275 times C, the number of defects. Right, so this is how S is related to C. The 25 minus 275C is the linear transformation. When finding the mean of S, right, because that's what we're finding, the mean and standard deviation of the selling price, the mean of S is equal to this entire linear transformation. The mean, right, a measure of position, is affected both by adding, subtracting a constant and multiplying and dividing by a constant. So the mean is affected by the entire linear transformation. So that means we get 25 minus 275 times the mean of C. And we use the mean of C to help find the mean of S. That results, we get 25 minus 275 times 1.2, and we get 2170. So essentially we expect a chip from Chipcore to sell for about 2170 on average, based on the number of defects, the expected number of defects. Right, so that gives us our mean. Standard deviation of S is a measure of spread. Measures of spread are only affected by multiplying and dividing. Right, so that means the 25, that constant that is being added, subtracted, it's not part of our calculation, right? We use the formula, the absolute value of essentially the constant that we're multiplying by times, right, standard deviation of C. That gives us 275 times 0.36, and that gives us 99 cents. And that is our standard deviation. So over the course of sampling many chips, we get a variance of 99 cents from the mean of 2170 on average. Is there anything else I can clarify here for you guys? This is the question that had the most errors. A lot of you guys did really well on question number 2 with the geometric and binomial distributions, but this first one seemed to give everyone a lot of problems. All right. Well, excellent. You'll be able to find a very similar workout to these questions already linked in Canvas on the calendar if you'd like to see this, and obviously it will be in the video recording of today's lesson if you'd like to hear me explain it. So with that, we're going to move on to our lesson for today on the beginning of chapter 7, specifically section 7.1. So we'll get that going here. Give me a moment. Where to go? Yeah. All right, here we go. So what is a sampling distribution? This is section 7.1. Chapter 7 is about sampling distributions. Right. If you don't know what a sampling distribution is, that's okay, because that's what we're going to learn about today. Right. In this lesson, we're going to learn how to distinguish between a parameter and a statistic. We're going to use the sampling distribution of a statistic to evaluate a claim about a parameter. We're going to distinguish among the distribution of a population, the distribution of a sample, and the sampling distribution of a statistic. We're going to determine whether or not a statistic is an unbiased estimator of a population parameter, and we will describe the relationship between the sample size and the variability of a statistic. So that's the goal for today. So the process of statistical inference involves using information from a sample to draw conclusions about a wider population. It's kind of the whole point of sampling and collecting statistics. We want to know something about a general population. Different random samples yield different statistics. We need to be able to describe the sampling distribution of possible statistic values in order to perform statistical inference. Essentially meaning taking one sample is not enough, right? Because we know that that one sample could yield a different outcome than the next sample, and that sample could be different than the next sample. So in order to get enough data to actually perform a statistical inference, we need to take multiple samples. Right, we can think of a statistic as a random variable because it takes numerical values that describe the outcomes of the random sampling process. So this is a visual of what sampling is, right? We sample from the population. Sample is a subset of the population. We collect the data from a representative sample. We make an inference about the population. That's the point. Okay. And we can think of the statistic as a random variable because out of each sample, I can essentially get one statistic that says something about the population, right? It could be the mean of the sample's heights. It could be the standard deviation from the mean. It could be the median income of, people living in a certain zip code, right? But that we get a single value out of that. And then over multiple samples, I get multiple different values, right? So each sample is like a possible value for a random variable. As we begin to use sample data to draw conclusions about a wider population, we must be clear about whether a number describes a sample or a population. So a parameter is a number that describes some characteristic of the population. A statistic is a number that describes some characteristic of a sample. Remember S and P. Statistics come from samples, S, and parameters come from populations. Right? So the first letter of each of these terms refers to where they came from. Statistic, sample, parameter, population. We write the Greek letter mu for the population mean and X bar, right? That's the little X with the bar, for the sample mean. We use P to represent the population, a population proportion. Okay, so we could say P equals 0.15 for the proportion of people over 6'5". I don't know, right? That would be a proportion. The sample proportion P hat, right? It's the letter P with the little circumflex above it. It's the symbol above the number 6 on your keypad. Right? And P hat is used to estimate the unknown parameter P. Right? P hat could be, or X bar could be, the value from our sample that could be an estimate of the parameter. We can't call it the parameter, and we can't call it the actual proportion for the population because it came from a sample. Does anyone need a moment to write anything down? Please raise your hand. So how can X bar be an accurate estimate of mu? After all, different random samples would produce different values of X bar. The basic fact is called sampling variability. The value of a statistic varies in repeated random sampling. To make sense of sampling variability, we ask, what would happen if we took many samples? Okay, so we take lots of samples from the population, and that gives us hopefully something we can use, right? But we don't know what that is until we do the sampling or a simulation to see what the sampling could yield, right? And hopefully that gives us something that's usable. Okay, does anyone need a moment to write anything down? All right. If we took every one of the possible samples of size n from the population, calculated the sample proportion for each, and graphed all of those values, we'd have a sampling distribution. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Right? So it's a distribution essentially of the random variable. We can think of it as a random variable that represents the values from each sample. Okay, and we collect all those, and that becomes the sampling distribution. In practice, it is difficult to take all possible samples of size n to obtain the actual sampling distribution of a statistic. Instead, we can use simulation to imitate the process of taking many samples. Sometimes the book will just provide you with simulation data. We will tomorrow look at an actual piece of software that we can access online that does a simulation for us. So simulations become very useful because it allows us to do lots of work in a short period of time. See, we need a moment to write anything down from this screen. So we have sampling distribution versus population distribution. There are actually 3 distinct distributions involved when we sample repeatedly and measure a variable of interest. The population distribution gives the values of the variable for all the individuals in the population. Okay, so each individual makes up a data point on the population distribution. The distribution of sample data shows the values of the variable for all the individuals in the sample. So again, individuals make up each data point in a sample. The sampling distribution shows the statistic values for all the possible samples of the same size from the population. Right, so it depends on the variable that we're tracking. It could be shoe size. It could be the mean of incomes, right? There's any number of things we could choose to be interested in and track, and then that would create the statistic from our sample that would then be collected to create the sampling distribution. All right, here's a visual. So we get the population distribution. So this example, or this set of distributions, is based on a activity where there are blue and red chips, like poker chips. There's an even amount of these chips in the population. Right, so you have a 50% chance of selecting red. So red is what we're keeping track of. So the variable is the color, and we're simply taking a simple random sample of 20 chips from this bag of 200 chips, it seems, and recording the color, blue and red, and the amount of each color that happens. So in our first random sampling, we had 8 red chips, 12 blue chips. That gave us a p-hat, right? So the proportion of red from our sample, so this is a statistic, p-hat is 0.4. The 0.4 is then recorded, right? It would be a data point in here on the sampling distribution. And this is actually a dot plot recording all the p-hats that were found, all the statistics. Right, we did another simple random sample, got a different p-hat, another random sample, different p-hat. All of those get recorded into our sampling distribution here. So that's how these things are related. Is there anything I can clarify? The fact that statistics from random samples have definite sampling distributions allows us to answer the question, how trustworthy is a statistic as an estimator of the parameter? To get a complete answer, we consider center, spread, and shape. Right. The center, we want to look for biased or unbiased estimators. In the chips example, we collected many samples of size 20 and calculated the sample proportion of red chips. How well does the sample proportion estimate the true proportion of red chips? P equals 0.5. So again, we have our sampling distribution of red chips here. Note that the center of the approximate sampling distribution is close to 0.5, right? That seems to be where the center would be, the mean or the median. In fact, if we took all possible samples of size 20 and found the mean of those sample proportions, we'd get exactly 0.5. So, a statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. Right? So in this example, because essentially the center, right, if we visually just look at the distribution, the center looks like it's in alignment with the parameter. That gives us information saying that this is an unbiased estimator. If for some reason this was skewed and the center appeared to be at like 0.3, we would have to say that this was a biased estimator, right? The values we got were not in alignment with the true value of the parameter. In this case, it is, so we say it's unbiased. So we need a moment to write anything down. So describing sampling distributions, the spread, low variability is better. To get a trustworthy estimate of an unknown population parameter, start by using a statistic that's an unbiased estimator. This ensures that you won't tend to overestimate or underestimate. Unfortunately, using an unbiased estimator doesn't guarantee that the value of your statistic will be close to the actual parameter value. Right. So in this example here, we see two different distributions, right, for the same thing, right? However, the one on the left here, we have a sample size of 100. So we did 1,000 samples of size 100, and we got this distribution, which looks approximately normal, has a center at 0.37, which is looking like the center of this other one as well. This one, however, used a sample size of 1,000 and did 1,000 samples of that size. Notice the variability or the spread of this distribution is much, much more narrow. This is because larger samples have a clear advantage over smaller samples. They are much more likely to produce an estimate close to the true value of the parameter. Essentially, because there's less variability, we are much more likely to get a mean sample proportion where it should be. Because there's more variability here, there's more wiggle room, it's possible that the mean might not work out. There are general rules for describing how the spread of the sampling distribution of a statistic decreases as the sample size increases. One important and surprising fact is that the variability of a statistic in repeated sampling does not depend very much on the size of the population. The variability of a statistic is described by the spread of its sampling distribution. This spread is determined mainly by the size of the random sample. Larger samples give smaller spreads. The spread of the sampling distribution does not depend much on the size of the population, as long as the population is at least 10 times larger than the sample. In other words, as long as the population satisfies the 10% condition. Right? Population, our sample size should not be larger than 10% of our population. Otherwise, things start acting differently, or they could start acting differently. So again, the main takeaway, large sample size, give smaller spreads. Make sure your 10% condition is satisfied. So then we have bias, variability, and shape. We can think of the true value of the population parameter as the bullseye on a target, and the sample statistic as an arrow fired at the target. Both bias and variability describe what happens when we take many shots at the target. Right, so there's essentially kind of like four basic ways that this can work out. We can have high bias but low variability. Right, so we had a nice high sample size amount, but unfortunately it was biased. Right, we can have low bias and high variability. Right, so this is probably all going to work out and give us a mean close to the bullseye, but our answers, our responses are kind of all over the place. High bias and high variability, it's just all around kind of off. And the ideal would be no bias and low variability, right? In the bullseye, very well, nice and clustered there. Right? And bias means that our aim is off and we consistently miss the bullseye in the same direction. Our sample values do not center on the population value, right? Which could mean that we maybe set up our sampling poorly when we put together our experiment, right? Maybe we were collecting our simple random sample in a poor location, right? There could be other reasons to create a bias. High variability means that repeated shots are widely scattered on the target. Repeated samples do not give very similar results. Right? We're getting things that are kind of all over the place and spread out. We have a less likelihood of doing that with a larger sample size. Right? So, do we need a moment to write anything down from this slide? So there you have it. That is section 7.1, right? We can distinguish between a parameter for a population and a statistic for a sample. We can use sampling distribution of a statistic to evaluate a claim about a parameter, right? We can decide, is this sample statistic biased or not? If it is unbiased, the claim about the parameter is probably true. Among the distribution of a population, the distribution of a sampling distribution of a statistic, all right? We need to be able to distinguish between these things. They are all three different, but they're all three related. Whether or not a statistic is an unbiased estimator of a population parameter, we have a visual way of doing that. And the relationship between sample size and variability of a statistic. Larger sample size, less variability, typically a little bit more reliable. And that's the end of that. All right, so that brings us to the conclusion for the lesson. All right, tomorrow we will be doing a Desmos activity that will provide us an opportunity to practice our understanding of these new terms and some of the principles covered in section 7.1. And then next week we'll be starting section 7.2 and possibly 7.3. I need to see how that works out. All right, is there any other questions or anything I can clarify for you guys before I let you go? Okay, well then with that, I will see you tomorrow, bright and early in the morning, and we will do our activity and have a good time. And then have a great day, and I'll see you tomorrow. Bye.